I was looking for a title that would kind of capture kind of the two endpoints in the Landsat program as a whole, the long and the short of it. The Landsat program, and I'll show a chart on that. It has a very long history. There have been Landsats in orbit since 1972. Yes, I got that right. Maybe I get a cookie from the Landsat project scientists for getting that one right. I was in grade school when the first Landsat went up in 1972, and I was still in there at the end of its mission in 1978. It was kind of an early demo. No one really envisioned that this would turn into a 40+ year program, and that we would have so many applications, and the economic benefits and societal benefits and the things people have come to actually depend on. And Landsat, around the Landsat 8 era, became written into public law that it would continue. We had to provide continuity of measurement because so many applications, say agriculture as a good example, had become so dependent on the data to get their maximum yield, manage crops and things like that. And so that became a strength of the program, and I'll show you some examples of that. In the short of it, I'll say this: we're working on the next generation Landsat, which we're calling Landsat Next. That's kind of the limit of our creativity, but we figured that was a little better than throwing another number out there. We continue the legacy and we continue the continuity, but we're also looking at the other end of the temporal spectrum, where we have users that want us to take data every day for things like water quality, where things can go bad in a big hurry when you look at things like algae blooms that occur, and that impacts people's health directly. And so and even in agriculture, there are reasons to do that. So we're trying to solve that problem while at the same time preserve this continuity of observation with a very stable, consistent observation, so that we can continue all the many varied applications that people have come to depend on. I guess I'll do a quick video here just to show how the current Landsats, 8 and 9, with 9 going up in 2 weeks, collect data. They do it in a manner that we describe as a push broom. So they look at almost a line on the ground, and it depends on the motion of the spacecraft in orbit, which is moving pretty sporty at 7 kilometers per second across the Earth, to build an image. And so we go around our orbit that we've chosen, and we've been in for quite some time, since Landsat 5, is a repeating orbit, polar orbit, that repeats every 16 days. So a single Landsat observatory comes over, well, unless you're way up near the poles, but close to the equator every 16 days. There are currently 2 in orbit, and so we have about an 8-day revisit rate. And right now, when we combine our capability with the European Sentinel-2, we're somewhere around 3 to 4 days on average for a revisit for a lot of these applications, which is great for agriculture and water quality. This is a sun synchronous orbit. So the sun is roughly in the same position every time we come around. And the Earth turns, but the orbit remains fixed relative to the sun, and that's how it gets mapped out. And there are a lot of advantages to that, in that it's a consistent observation. So you take out the confusion of going over at a different time of the day or looking from a different angle. And so it becomes very sensitive to change on the surface. And so it's, when you're looking for conversion of land cover or migration of, different plant species in response to a warming climate, say, we're very sensitive to that because of the consistent observation and a very robust calibration plan. This is the short list of applications that are supported by the Landsat data, and it makes for an interesting, challenging job on my part to try to satisfy as many users as possible on a fixed budget. And so, and that's really the trade space I'm working in, because we have, like in the Landsat Next, we have a lot of possible ways to implement the mission in terms of the instruments and how we fly them, the orbits we pick, and we are evaluating, kind of our maximum return. And it's this list and a few others, and we kind of put a metric as to which of the architectures is going to give us the most bang for the buck, if you will, or highest return on investment. A lot of the things here, I would say, when you look at things like change over a long period of time, that's where the continuity of our 40 plus years comes into play. But things like evapotranspiration, and that's how plants basically sweat to cool themselves down, and it's an indicator of how much water they're using and the plant health. And there's another video later to talk about that. And those are immediate things. Farmers want to see that. Forest managers, for instance. These kind of long-term trends for land cover, for various reasons, agriculture is mixed into there, and agriculture and what's planted, what kind of crops, that's driven by demand and economic forces. And I have a video here that really shows that well, that I'll show you in a few minutes. Water dynamics, flooding, and this is another one of those short-term drivers. We really like the ability to get access on a daily basis to look at water inundation from floods and how things are getting back to normal. We also look at before and after and damage from floods, and so that's kind of the midterm use of the multiple imaging that we do. The geology, natural resources, that tends to be not a big driver for the frequency, because the rocks don't get up and move very quickly. So we aren't driven as much to get back there frequently for that. Just a quick video on the various ways that the Landsat data are used. And I say quick, this is the person who put this together, they liked really rapid transition, so it's not very long. I think it's a minute and a half or less. Yeah, 140. There's supposed to be an audio track for this, and for some reason my plugin that supports it with PowerPoint did not let the audio come through. I gave up on trying to troubleshoot this one. But this just shows you some of the applications that have depended on the long term, like the urban growth. Food, we look at the instantaneous health, on that day of the crops, how green they are, the chlorophyll, the productivity. Of course, natural hazards. We get in there and watch the spread of some of these hazards and actually assess and detect where they've been in historically, and whether we need to be careful in the future where we locate our developments and things that we care about. There was a mention here that the Landsat data is free to everyone, and that's had a tremendous impact in the utility and the growth of, let's see if I can get this to advance. Here we go. The ability for little applications and applications we've never thought of. Like now you can get the software if you're a farmer and put here's my mouse, and download the data for free. You can do your own assessment of your own fields, for instance, without having to pay. It used to be hundreds of dollars per scene, and now a small farmer with a mid-sized farm can do their own assessment for crop stress and where they need to put more water, maybe change their fertilizing of the fields. So there are thousands of applications that emerged when we made the data available to everyone for free. One thing I want to show you before I talk about the color or the wavelength, the different bands that look at the Earth in both the visible and the invisible spectrum. It's just notionally the sun, which we call the bands that see the reflected light from the sun, the reflected bands, is very hot. And so most of the output of the sun is in the visible spectrum, and you can see there's my mouse. You can see that your expected color spectrum there. And as you go out, you get into the invisible spectrum, and there's a lot of information out here, and it gets much harder technically to detect that. The materials that we use, there's a limited number of materials that can sense light out there. And when you get down here, this is the energy given off by an object about the temperature of the Earth. It's about 300 Kelvin. And we look here to measure the temperature of the Earth. And so we need a completely different set of whoops, I'm sorry, I wanted to advance. There we go. And on that note, the early in the program, the multispectral scanner on the first Landsats, it was only the visible plus near infrared, so it's kind of just outside the range of animal human vision. There's a lot of information, particularly with vegetation and crops, and so it was launched basically in this range, and the detectors work at room temperature, and but it was still revolutionary to get images of the ground like this. In future ones, we started to narrow up the bands, so we were more sensitive to some of the color features, the subtle color differences between surface types. So we can say, oh, that's a deciduous tree, that is an evergreen tree, that's corn, soybean. So we, as we added more spectral bands, color bands, we were able to separate out things into their categories better. And then we started to look out into the shortwave infrared, and that provided a lot of information about like the kind of the structural part of plants, the cellulose, the woody parts, the litter that's left behind when you do a harvest, and it's really these bands in here, and there's information on other surfaces, but when you combine this with the stuff that you can see visually, which is down here, your blue, green, red, in the spectrum, you can then, I put it in quotes, see things about the surface that you cannot see with the naked eye. And then we add the thermal, and that makes the Landsat program unique. The European program only covers the visible and then these invisible reflected light from the sun. The thermal allows us to do things like look at how the water content, kind of the process going on in plants in particular, and very important for U.S. agriculture and also water rights management in the West, because water is such a great, valuable commodity. What do we do with that? You pull out these bands, these different color bands, including the invisible ones that you can't see with your eye. Depending on how you combine them, it brings out information about different surface types. This is going to be really familiar. This is what we normally do. This is what the camera in your phone or your digital camera does. It's in your eyes too. It's red, green, blue. You're familiar with the three color. And this is not a false color. This is a natural three color composite. So it would look like the color you would see flying over from space. But when you then go and start pulling in some of the invisible bands that you cannot see with your naked eye, you pull out other information. So in this case, you have one visible band and two invisible bands combined. And so you're actually pulling out some of the information related to kind of the plant structure, a lot of the woody components. And when you talk about, like, burns really stand out with this kind of a combination here. And so this is a different aspect of the vegetation in this case, and you're getting some contrast about right near the surface of the water. And then in this case, it's pulling in yet another combination, one invisible band, and then green and red. And this combination is really to exploit vegetation, or not exploit, but to make it really stand out. And so when you process the data by subtracting and then dividing by, the bands, another band, you increase the contrast of what's unique about vegetation versus everything else. So you notice, like, urban surfaces just all go to the same color. And the more intense the red in general, the more healthy, the greater the chlorophyll concentration in the plants. And so it's a quick way to assess how a field is doing and a farm is doing. So this just shows, as you go by, you get different information by combining these color bands, if you will, including colors you can't see, if you want to describe it that way. I'm going to go ahead and step forward. So getting to the point, long term, we use the Landsat data to look at what's happening in terms of trends over years and decades. And so when you look at these agricultural types, and each color here, and I did not put the legend up here, I apologize for that, but each color here represents a different crop type. And you see the San Joaquin Valley has probably the highest diversity of crop types in the country, coming out of the breadbasket of California. And as you move around the country, you go to Texas. I believe the orange is citrus, but I'd have to see what it looks like over in Florida. But there's a little bit of citrus in the San Joaquin Valley, Southern California area, and then down at the bottom of Texas, and of course in Florida, as everyone knows. Up here, you're looking at kind of the blend of soybean and corn as the dominant crop in the Midwest. Now, this would be, what do we have here? The Dakotas. And I found this very interesting. I didn't realize there was such a diverse agricultural area in this particular part of the South. And honestly, I can't tell you what it is, but and so we look at how things are changing, and a lot of times you can correlate this information, the U.S. Department of Agriculture does, with economic forces or changes in demand for different kinds of crops. And so it helps in planning, and in the commodities market, what's going on, what's planted, what's the demand out there, what do you think corn's going to cost in 2 months? So, and related to that, well, I'm sorry, this is out of order. We look at land conversion. What are the forces? What drives the development of urban areas? And in some cases, the urban areas overtake the local agriculture and the farms disappear. You see in the early part of this for Phoenix, at first, the agriculture expanded. There were more, the red are the really high chlorophyll content, healthy crops. And then kind of an urban growth overtook that, and they kind of pushed the agriculture right up against the base of the mountains. And so, Phoenix is now dominated by the urban development and not the old. They used to have a lot of fields surrounding there, a lot of irrigated farming. So you can really see how the forces are in the urban growth. We look at changes in the Arctic as an indication of what's happening with the Earth's climate, and are just trying to understand those processes. And this is 30 years apart from different Landsat imagers, but they've been cross-calibrated. And one thing you notice is that this glacier has really retreated and fallen apart over that time. And there's been this is actually the main ice sheet you see in the bottom of this image. I was going to I won't play it. I don't think I have time. There's there's lots of stuff out there where people looked at this. These are ice flow rates. This is how fast the ice, because the glaciers are rivers of ice, and they're always flowing and heading out to sea in many cases. And one of the things, besides the receding edge of where the glacier dumps out into the fjord, is early on things were pretty cold, so there wasn't a whole lot of motion here. Things were frozen solid, and you take subsequent images and you basically look at what's moved. You measure, you track features on the ice and estimate the flow rate of the glacier. It's like a real thick syrup flowing out to some degree. And one thing you notice over time is that the rate of flow in this particular glacier is increasing and you can see it up on the ice field. The motion of the ice field is starting to become more apparent. Things aren't frozen quite as solid as they were in '86 as you move through time. And they've picked a point in the glacier, and there's a time series of the flow rates. So you just do a series of images, and you lock yourself to the mountain peaks, which aren't moving, and then you can look at how fast that ice is flowing. So it's an important thing for trying to look at the impact and what's going on and estimate how much ice is going to be dumped out into the ocean. Midterm observations. Here's a video. There's actually audio, so I'll probably shut up for this one. For fire recovery, this is actually the current Landsat project scientist talking about the use of Landsat for looking at burn scars and recovery of forest. Well,
Phil, it doesn't sound like the audio is coming through very well.
it's not. Oh, I'm sorry. Okay, well, I will speak to this. You see the recovery. Let me get this going here. And you can see where the burn scars are, and you can see the vegetation recovering. And so it's very important for looking at the management of the forest and understanding how things recover after a fire. Short-term observations, this is where the daily, near daily observation is very important. When you look at trying to predict crop yields, it's very important to know when things were planted, when the plants emerged, how fast they became green, and then when they were harvested. And then also, did they replant that field? And if you look closely in different areas in here, you can actually see it. In this case, the greenness indicates how much chlorophyll and how green the plants are getting. But this is important data that goes into estimating crop yield across the country and the globe, and predicting, say, famine in other countries before someone comes knocking at the door asking for some help. I mentioned the evapotranspiration. That one of the things that we get with Landsat is we get surface temperature, and that's where the mouse is over here. We also get the reflectance, or how much light that these surfaces or the different fields are absorbing. And so you can predict when the sun's out how much, based on how reflective the surfaces are, how much they would normally heat up if there was no way to cool it down. But that discrepancy between what you would predict based on its reflectance and how much sunlight's coming in, and what you actually measure in temperature through some formula yields this estimate of how much the plant is cooling itself down by perspiring. It's called evapotranspiration. And so that's an indication of the health of the plant, and also an indication of how much water the plants are pulling out of the ground. And when you're a water rights manager trying to decide, did that farm get enough water? Did it get too much water? How do we manage the take of water out of, say, the Snake River or the Green River in the West? Water quality. This is another area where we'd like to get the revisit rate up, because things change rapidly. Things like mineral runoff, phosphates, water temperature, a lot of things can make things blow up into a bloom that's actually unhealthy. And so there's a product pulled out of the different color bands that gives us a measure of the total chlorophyll in the water column. And that, unfortunately, right now, we just know there's a total chlorophyll. We don't have enough color bands to then identify the type of algae that's contributing to that. And there are some that are very harmful to people and the fisheries that we would like to be able to detect and give people a heads up to be very careful, or don't drink that water, or don't take fish and harvest from there, because you could get sick. Another example of that is, the sediment runoff. This is coming off in South Carolina after a heavy rain or flood. All of that sediment going out into the near shore ocean really impacts the fisheries. It impacts the quality, the whole food chain for a while. And so really being able to understand that and furthermore, maybe manage that further back up in our watersheds and the discharge is very important. And this changes rapidly, right? You get a heavy rain, a flash runoff, and so we would like to be able to look at this on a daily basis and watch this change. And these sediments feed some of the blooms that I spoke about. Instruments, they become quite large when you go out to these longer wavelengths, into the shortwave infrared and the thermal. The size of the telescopes have to grow to get this resolution. And so the mirrors are large, and very important to us is the smoothness and the cleanliness of the optics, because often we want to look into the water, say, that's fairly dark, and right close by is a bright shoreline of sand or maybe even snow cover, but and that's not our intended target. It's kind of like when you're trying to drive your car and you have dust or a dirty windshield and the sun's rising, it just blinds you. And the same thing is true here. So a lot of effort is done to keep everything very clean and pristine. Lots of detectors. We have thousands of light sensing elements across each one of these color bands. And so you end up with a very large focal plane. It's not like the detector in your camera that's smaller than your pinky nail. So that these are technologies which, in some cases have to be developed, and they're driven by our requirements and what we write down to say this is what we need to measure for the science. Instrument put together, this is the reflective band imager that looks at the reflected sunlight on Landsat 8 and 9. We rebuilt the same imager for 9, and it's quite large. And so and then the thermal imager that flies along with it to give the surface temperature is also fairly large. You see one of the technicians or engineers standing next to this imager. And so you end up having to put this on a fairly large spacecraft, and you end up with something about the size of the shuttle bus that takes you, to your parking space, or not quite a school bus, but not small. And so, you end up needing a large rocket to throw this into an orbit that's 705 kilometers above the Earth. In this case, it's the Atlas V that's launched and operated by United Launch Alliance. How am I doing on time? I'm sorry. Am I out of
You're
time?
okay. Yeah, you're okay.
Okay. All right. This is a simulation that was done to show the entire, launch sequence for 8 and 9. It's going to be on the same pad, same rocket, so it applies. This was done for the Landsat 8 launch. It used to be called the Landsat Data Continuity Mission. A long, tortured political history on that. We renamed it Landsat 8 when USGS got the keys. NASA builds this and launches these observatories for various other agencies, in this case, the US Geological Survey. And about 3 months in, after we're sure everything's working very well, and we work with them to do that assessment, we have a big event where we kind of hand the keys over and say, here you go, have fun with it. And they operate it, collect all the data, and calibrate and disseminate it to the users. So we have a very good working relationship with the different agencies. NASA also does this for NOAA with the weather satellites. We build and launch those, and we literally hand over the keys after things are on orbit working well. There's actual footage of the Landsat 8 launch from Vandenberg about 5 years ago. Actually, we just passed the 5-year anniversary. I wasn't this close because I'd get fried, but I was about that far away, and I could feel the heat off the engines. The engines pulsate at a certain frequency, and as it arced over, it felt like someone was just thumping on your chest with a, with one of those foam bats, and it was quite an experience. I'm looking forward to the next launch because we've worked on this second one for quite some time now for Landsat 9, and we'll add capability. Some of the unique color bands that were on Landsat 8 that were not on 7 will now have 2 of them in orbit with the same complement of spectral bands, color bands, both visible and invisible. So anyhow, let's see where this one's at. Yeah, it just kind of flies out of sight. You've probably seen this kind of footage with the shuttle where they track it as far as they can with those special cameras. And then finally, this was taken from a camera that was mounted on the spacecraft, sending images back. And you could actually see the Landsat 8 observatory and its booster stage make a separation and be sent on its mission and inserted into the orbit. And in the animation, you can see all the stuff has to fold out. Well, in the animation, it showed it happening rapidly, and it's a long process to make sure it gets to orbit and it's healthy, and you don't turn on all the switches at once. So it literally takes 3 months before we're confident that this is scientifically sound, that the imagery will be useful for the applications in the science. And the people who build the spacecraft and do that part, they get about a month to make sure the spacecraft is working the way it should, and test all the systems. And we actually heat things up and bake out all the contaminants to make sure those mirrors and optics stay really clean. So it takes a while.